Okay, so here's where we were last time. We were applying, trying anyway, to apply the idea of a scalar surface integral. Let me remind you what that was. Here's our idea of a scalar, I said surface, a scalar line integral, right? The idea of a scalar line integral is the whole is the sum of the parts as accumulated over a curve in space. But it's still chop it up, add it up, and a lot of the same concepts apply. So we were trying to apply this idea to this, here it is, this very different situation where we're computing work. And at first, it kind of seems like a reasonable, this could work kind of a deal, no pun intended, because if you look at a little piece of curve, right, on that little piece, well, the little piece of curve is approximately straight, as required to use that formula. And the force is approximately constant. Close enough, goes away in the, round off arrows go away in the limit. And so, it feels like we could just say work is force dot displacement. So in fact, we can kind of flesh that out a little bit here. Here's that little piece of curve. And we can talk about the displacement differential, position differential dx as our displacement, and we can talk about the force F and force dot displacement. Boom, that'll compute the amount of work that it takes to move along that one little piece of curve, and then we take that a little piece of work, add that up over the entire curve. Right? So as usual, we take the entire curve, add it up, and that gives us the total amount of work. Nothing wrong with that, so it seems. So what we have to recognize, though, is there are some key differences. For one thing, notice we did not end up with a scalar line integral. Right? This is just not. Right? It's importantly different. Look at this. Our differential no longer a scalar. Now our differential is a vector. Weird. Right? Definitely different. And furthermore, our integrand also no longer a scalar. Now we have not only a vector differential, we have a vector integrand. And I like to point out further, the multiplication that I do between them is a vector multiplication, namely the dot product. So this is a pretty different expression, even though it, we came about it by the kind of the same sort of chop it up, add it up approach that gave us scalar line integrals. Okay, so here's some other key differences. So if we're computing work, and in particular we've been asked to compute the amount of work that it takes to move along this curve like that, notice I have to say specifically which direction am I going along the curve. Am I going sort of up and to the right, as I have drawn here, or, did I mean perhaps instead to go down and to the left, like this, right? Same curve, but they're very different in terms of how work is calculated. So this is a big difference. I made the observation last lecture that when you're doing a scalar line integral, doesn't matter at all which direction you add up the things that you're adding up. It's just commutativity of addition, right? You can add up a bunch of little pieces of mass in whatever order you want. It doesn't matter at all, right? And so again, very different in this scenario. The order matters. So the way we're going to address this is I'm going to think of the domain here not as being just a curve. A mere curve is it's like a road. It just sits there. You can drive either direction along it. It's just a bunch of concrete on the ground, right? We're going to consider this now instead what we call an oriented curve. The orientation meaning not only do I have a curve, but I have an attached, required direction that I have to go along the curve of the two choices. Okay, so this is not the same as a curve. It's very closely connected, but it's a different construction that we call an oriented curve. How are we doing? Everybody on board with that? All right. Okay. All right. So, how do we compute these vector line integrals? Well, you may suspect that the pictures and strategy that we use to compute scalar line integrals might come into play. Here's a reproduction of all that stuff. All the objects that we talked about with scalar line integrals are all represented here in this picture and algebra. And yeah, everything we need is right here looking at us. So if I want to rewrite vector line integral, in particular, I'm going to need to know dx and how to rewrite dx. Well, there it is. And here are 3 pre-established formulas, alternative ways that I can think about dx. And so I can just plug them in. And that gives us 3 alternative formulations then of vector line integrals. Take your pick. These are all equivalent. Coincidentally, we already had everything that we needed to do the pullback. I mean, we are in fact doing a pullback here. Just we didn't feel like we had to earn it because we already earned it. Okay. This is the one that we're going to focus on first, and that is, notice this is a dt integral. So this is the one that has been pulled back. This is the one that is a single variable integral, right? Integral from a to b on the t-axis. This is a single variable calculus plug and chug. So this is the one we're going to use first. So let's dive into it. We're going to compute the amount of work that it takes to accomplish a certain task. That is, we're going to be walking along a certain curve, and there is a force involved. We have a formula for the force that's given, and how do we compute work? Now, before I get into the plug and chug aspect of it, there is a little twist. It's a little physics twist. This is something that presumably any of y'all who have had a physics course before have seen, I assume. It's this idea of equal and opposite forces. So, easy example, if I hold my stylus up here with my hand, right, it's not accelerating. F equals ma. So if it's not accelerating, it's tempting to say there's no forces on it. And that's not true. There's actually 2 forces on it. Gravity is pulling it down. I am pushing it up. The total force is 0 because it's not accelerating, right? But saying that the total force is equal to 0, another way to say that is that the 2 forces that are applying to it are negatives of each other. So thus the equal and opposite terminology. When you have a situation like this, you have to look at the phrasing of the question, think about what you've been asked, and identify whether the force you've been given is the one that you need, or if it's the equal and opposite. Namely, might it be the negative of the one that you need. And in fact, that's the case here. So we were given, notice, the force that the wind exerts. The wind is exerting the force F. We were asked to compute the amount of work that it takes you to perform as you walk resisting the wind. Right? So if the wind is blowing this way on you, you have to lean forward and push that way against the wind to keep from falling over. So the force that we need, the work that we're exerting, is the negative. It's the negative of the force that the wind is applying. Does that make sense to everybody? Okay. It's an annoying little reality of physics that you always have to, and it's all about the phrasing of the question. So don't make the mistake of just assuming that whatever force was given, oh yeah, you put that and that's the integrand, and just plug and chug. You do have to analyze the phrasing and make sure that the force is actually the right one. So just be careful about that. Okay. All right. Now that said, we now have a line integral to compute. Line integral to compute. This is going to be largely plug and chug at this point. We we know that our curve is counterclockwise, top half of the unit circle, and good news, counterclockwise on the unit circle. We already know how to parameterize that. Right there. This is our old friend, right? One of the very first parameterizations we ever wrote down. Yeah. So that's the formula we're going to be using here. We're going to be computing this vector line integral by using this formula here that you'll notice everything's written in terms of the parameterization. So this is, you might say, pulling back through the parameterization. And to pull back through it, you need to know what that parameterization is. Yeah. Okay. So there's our parameterization. Easy derivative to take. Oh, real quick. Why is t only from 0 to pi? Well, specifically, we are moving only along the top half of the unit circle. And if you think about the values of t that take you along that top half of that unit circle, t goes from 0 to pi. Okay. Okay, and now it really is just a matter of plugging it all in. Here's our formula, right, established on the previous page. We computed x prime a little ways back there, bottom of the previous page. We were given this formula for f right here. That was in the statement of the question. Now be careful here. That is the force that was given. That's the force that the wind applies to us. Don't forget, we do need this minus sign here to carry through, right? I mean, that minus sign doesn't go away. But also be careful. Don't accidentally double count the minus sign. This happens more often than you would think. That students will look at this formula right here and think, wait a second. I don't want to write down the wrong force. I'll write down the negative of the f because of, same reasoning, and they get a second minus sign. That, of course, cancels the first, and, of course, that's wrong. Okay, so just remember, the minus sign's already been dealt with. Last remaining issue is what do I do with x and y here? And I'll remind you, whenever you're doing a pullback, whatever you're pulling back through is what tells you the formulas for those coordinates, x and y. And you can see it right here in the formula for the parameterization. X is cosine t, y is sine t, and we can plug those directly in here. And let's see here, x is cosine t, whoops. There we go, x is cosine t, and y is sine t. Everybody on board? Okay, and it's single variable calculus from here on down. And I'll let y'all work out those details. Make sure that you're comfortable with all that, of course. Pausing. Questions? Okay. Good deal. Okay, so now let me scroll back up to where we were, let's see, last time. We had this formula here for how to pull back through a parameterization with a scalar line integral. The very first observation I made, handy fact, use whatever parameterization you want. Parameterization doesn't matter. Parameterization is just a different way of chopping it up. So, of course, they're always going to add up the same no matter how you chop them, so chop them however you like. So parameterize however you like. Now, there was mathematically, there's more to it than that, but that's the intuition. It's very satisfying, but it's nevertheless a good thing to have noted. So we might reasonably ask here, is it the same? Can I say that the parameterization doesn't matter? And there's kind of an asterisk on this. What you have to remember is that when you write down a vector line integral like this, you write down a vector line integral. The integrand is not a curve. Easy to forget, easy to lose track of. Very importantly, the domain is an oriented curve, not just a curve. So yeah, you can parameterize the oriented curve domain however you like, but it is in fact an oriented curve, and so any parameterization of it has to respect that orientation. So you do have to make sure to always parameterize in the same direction that the curve is oriented. Other than that, go crazy. Do whatever parameterization you want, just so long as it's going the correct direction. Are you okay with that? Now, what happens if you go the wrong direction? Well, if you go the wrong direction, all of your little dx's are going to be backwards. So, for example, looking at this picture here, looking at this little piece of curve, if you go the correct direction, then your differentials are, your dx vectors are like that. And if you go the wrong direction, well, your dx vectors are like that. They're all the negatives of what they ought to be. So, that means you're going to be off by a minus sign in every term in the summation. That means you're going to be off by a minus sign in total. In other words, you'll get the wrong answer. But here's another way to say it. Not only will you get the wrong answer, you will get a predictably wrong answer. Now, to state this completely, I'm going to introduce a notation. This is the book's notation. A superscript of a minus sign is going to be our notation for if I want to take a curve but orient it the opposite direction. And with this minus sign, minus sign notation noted, when you do that, when you go the wrong way through a parameterization, you're just going to get an integral value for the integral that's off by exactly a factor of -1. Is that cool? Now again, there's two different ways you can think about that. You can think of it as, okay, it's wrong and this is how wrong it is. Another way you can think of it is that, hey, you're allowed to parameterize the wrong direction. Just recognize when you parameterize the wrong direction, you're going to be off by exactly a factor of -1 and just fix it by sticking in an accommodating factor of -1. And then you're good. And I'm going to show you an example of that in just a second here. Okay. Everybody on board before I get some examples? Right. Okay, so we're going to revisit that example that we looked at previously, top half of the unit circle, vector field, forces, work, all that business. This time, though, we're going to go clockwise. So that direction across the top half of the unit circle. This is not the same oriented curve. This is a different oriented curve, right? Different orientation in particular. Now, how do we parameterize this? I'm going to show you two different ways to parameterize this. Well, let's see, I guess I should say I'm going to show you two different rationales for finding a parameterization for this. Here's the first one. Let's think of this right there as being the angle T. If you think of that as T, then at T equals 0, we're here. As T increases, we go that way, and when we get to T equals pi, we're there. And notice that, as required, takes us clockwise across the top half of the unit circle. So viewing this angle as T and then just doing the ensuing geometry will give us the parameterization we want. Now, how can I use that angle T to define the position of this point? Can I use polar coordinates? Well, not really, because that's not theta. This is not theta. Any formulas that you want to use from polar coordinates are in reference to theta. This isn't it. But it's easy to write theta. There you go. Pi minus t is theta. And with pi minus t noted, and keeping in mind that r is equal to 1, I can just immediately write down that this point, x comma y, cosine theta comma sine theta, just make sure that you actually put theta in there, not t. How we doing? Everybody okay? Right. Okay, now, bother. I need to rewrite this in a more convenient way. Trig identities, symmetries, angle addition formulas, whichever way you want to think about it. But these can be rewritten like this and that. Make sure that you're good to go with that stuff. Now, I think it's a good idea for everybody to know the angle addition formulas. They just keep being useful, and they will continue to keep being useful. It's hard to predict when they're going to be useful. They just are useful a lot. So I'm a big believer in the angle addition formulas. Given you all that speech before, but anyway, We're going to assume and expect that y'all know the angle addition formulas and that you can use those to do this. But of course, you can also just understand the symmetries of the cosine function. This is a standard, a standard symmetry of the cosine function, and likewise this of the sine function. Okay, now that's method number 1. Now let me show you method number 2 for how to parameterize this curve. Again, keep in mind, going clockwise across the top half of the unit circle. Here's the clever idea. That parameterization, missed, is a reflection over the y-axis of this parameterization, which I already know. That's just a convenient observation, right? You won't always get lucky like this, but you'd be surprised how often something along these lines might be useful. And once you make this observation that, the blue parameterization I want is literally just that purple reflection of the green parameterization I already know, then you can write down the green one. We know that reflection simply introduces a minus sign on the x-coordinate, as is clear from the picture, and we win. So we get the same formula that we got by the other argument. Everybody all right with that? The reason I'm showing you 2 different ways to answer this question, or I should say 2 different ways to parameterize this curve, is because these 2 different tools are useful in different circumstances. Sometimes this one, or a variation of this, makes sense when this one doesn't really fit, and vice versa. So it's good to be aware of both of these tricks, be on the lookout for opportunities to use both of these tricks. Sometimes it might be one or the other. Okay. And then once you have the parameterization, then plug and chug, just like on the previous page, and you get your answer, which is minus pi. Yes?
Do we change anything about the bounds of the integral? Do we change direction?
No, so your new parameterization, right, going like this, where this is the formula, it remains that I'm starting where t equals 0. Now I have a new notion of what t is, right? But I still start at t equals 0, and I still end at t equals pi. It's just that's interpreted differently on the picture. Is that cool? Yeah. All right. Okay. Now let me show you the third way to do this. The third way to do it is what I was hinting at on the previous page. We observed here on the previous page that if you orient in an opposite direction, that'll give you a minus sign on the value of the integral. And here's how we use that. This new curve that we've been asked to do a line integral on, that new curve is just the opposite orientation of the old curve, C, on which we already know the line integral. This opposite orientation gives you a minus sign. This is the theorem from the previous page. And once I have that minus sign noted, then I can recognize, I already computed that integral right there. Again, on the previous page, I computed the value of that integral was pi, and boom, there's my same answer, minus pi. Same answer that we got from above. Everybody see how that works? Okay. All right. So 3 different options for how to do that. Okay, now now we have a conceptual discussion to have here. We've only done one application so far of this expression, this vector line integral. Well, this expression, this vector line integral, is useful for a lot of other things. And the next example I want to give, I think, is a pretty easy segue. Where did we get that this was equal to work? Well, we got this interpretation by viewing the integrand as representing forces. And that's one of our standard points of view on vector fields. Vector fields can represent, among many other things, vector fields can represent forces. Well, if F is a force, then this is work. Fine, old news. Here's the question I want to ask. What if this vector field no longer represents force? What if it represents the velocity of a fluid flow, for example? Well, now what does a vector line integral represent? It's not work anymore. It's no longer force dot displacement. Now it's velocity dot displacement. And does that ring any bells for us? Not really. So if I find myself in some sort of a situation where I've got a vector field representing a fluid flow, this is a very normal scenario, right? I've got a fluid flow. What does a vector line integral represent in that case? And at the moment, we don't have an answer. Okay, so the way I'm going to answer this question, it's going to be kind of backwards rather than just directly computing. What I'm going to do is I'm going to ask a seemingly irrelevant question. I'm going to ask a question out of nowhere. And in the process of answering that question, what we're going to find unexpectedly is that line integral is going to show up as part of the answer to that question. And so that will give us an opportunity to make an interpretation. So this is going to take a few minutes. Bear with me. There is a punchline at the end. But for the moment, it's going to seem like we're just answering a random, weird physics question. This right here is all recopy from a few pages back. Nothing new here. I just like to have that for convenience of reference. And here's the new physics question that we're going to ask. It's a strange one. Suppose I have a curve. And suppose that I consider what I'm going to call a tube around that curve. This is a weird thing to want to do, but again, just bear with me. There's a tube that goes around my curve. And the idea of this tube is that if I take a cross-section perpendicular to the curve, anywhere of that tube, that cross-section will be some shape with area A. All right, does everybody see what I mean by this tube? All right. So, the weird question I'm going to ask with this context being given, it's going to seemingly come out of nowhere. It's not going to be clear why I would want to ask such a weird question. Again, bear with me. Looking at all of this fluid. Now keep in mind, we have a vector field in play, and the vector field represents flow of a fluid. So there's fluid inside of this kind of tube. Altogether, to what extent is that fluid flowing along the curve? And what I mean by along the curve, let's recognize that the actual flow is like this. I mean, to some extent, that's a flow along the curve. It's along the curve by that amount. It is perpendicular to the curve by that amount. Right? And the actual flow of the fluid, not necessarily parallel to the curve, but I only want to talk about the component that is parallel to the curve. And again, I grant you, that's a weird question. Right? So altogether, looking at all the pieces of fluid and altogether looking at the amount that they're flowing along the curve, what is the total of that amount the fluid's flowing along the curve? So the way we get our hands on that, we look at little pieces of fluid. Here you go. Here's a little piece of fluid. That's the amount of fluid. I'm going to call it dV. That's the amount of fluid in some little small bit of the curve ds. That dV, cross-sectional area times ds. Just looking at the shape, we've got a certain cross-sectional area there. A thickness is the length ds along the curve. What is this component? How do I compute components in the direction of a curve? Well, components are computed as dot product with the unit vector. Don't forget my tangent vector t, my unit tangent vector t, is a vector it's a unit vector that is parallel to, namely exactly along the curve. So that's how we compute that component. And so the combined extent of fluid flowing along the curve, right? That total rate, I'm just going to be adding up a bunch of things that look like this. Just component times dV, which again, you plug in the algebra, the geometry of the picture, you get F dot T times ADS. That's just how the details work out. And all together, plugging that in here, adding up over the entire curve. Let's see, my picture's getting a little out of hand here. Let me erase all of this. All of this going into there. Notice that the A is a constants factor outside of the integral. And altogether, here's my answer to the weird question that I have asked, and still don't really quite see why I'm asking this question, but the answer is that expression right there. How are we doing? Everybody with me so far? Everybody see that algebra? Yep. Yep.
What are the units for the flow rate?
We're not going to deal with units. The definition that I gave of F is that F represents velocity. So it's distance per unit time, but we're not going to pick units. That's somebody else's problem. Yeah, the way I like to always do that when you do get to actually writing down units and this kind of thing is pick a set of units, like have all of your distances in meters, right? Have all your times in seconds. Don't use hours and seconds. Those are incompatible, right? Just all time is going to be seconds, all distance is going to be meters. Pick a consistent set of units, and then everything works out. Yeah.
I'm just a little bit confused as to what Q would physically mean.
Oh, totally. No, you should be. Yeah, absolutely. No, let me explain what I think is going on there. So, what we're accustomed to is that when we compute some physical quantity, that we have a intuitive sense for what the quantity is first, and then we compute it on the basis of that intuition, right? So, for example, when we computed work, we said, we have some sense for what work is. We talked about, force dot displacement. We talked about why that makes sense. And then any computation that followed was based on that intuition. What you're experiencing right now, I believe, is related to the fact that this thing that I've asked is not a familiar physics concept. It's just not, right? This is a new thing. And again, the reason I'm asking it is because this is going to end up not being a question. It's going to end up that this is going to be an answer to a question. The answer to the question that this is the answer to is, how do I make sense out of what a vector line integral is in a fluids context? And I haven't quite gotten to the point where I've made that connection yet. So let me make that connection, and then that might give you some satisfaction. Is that cool? Yeah. Sure. Yeah. Okay. All right. So we've got this mysterious quantity Q. We're not clear why we're computing it, but we see that a vector line integral is part of the answer. And so I can use this to make an interpretation then of what a vector line integral is. Now the asterisk, I have to recognize that there's also this business about the cross-sectional area. I mean, that is an important part of the answer. I can't just sweep that under the rug, right? So I'm going to point out, though, that it appears as part of the answer in a pretty simple way. The bigger your cross-section is of your tube, the more fluid there is. Twice as big a cross-section, you're going to have twice as much fluid, and therefore twice as much of whatever it is this thing is that we're computing. So I'm going to interpret this as something that I can move over here into a denominator and say, obviously everything's proportional to area. So I'm going to express my answer as per unit area. What I have is an interpretation of this green line integral. And so here we go. The line integral, vector line integral of a fluid flow tells you per unit area of cross-section, to what extent is the fluid flowing along the curve? The total combined extent the fluid's flowing along the curve. So that's just the answer to the question, as it turns out, is this is what a line integral represents in a fluid context. And it's not a familiar concept, right? This combined extent that a fluid's flowing along a curve, kind of a weird thing, new idea, but it's a new idea that is what a vector line integral is. Is that satisfying at all, I hope? It's a weird circumstance, but very often when you write down mathematical expressions and you need to find, what does this thing mean physically, sometimes it's a new physics concept that you just have to kind of get used to. So here we are. All right. Alrighty. So let me show you a related idea. This is the idea of circulation. It is an interpretation of vector line integral. Here's our vector line integral. Again, F is representing a fluid flow. And the particular case that we're going to entertain here is that of a closed curve. So I emphasize what a closed curve is. It starts and ends at the same point. So for example, this curve over here, if I view this curve as starting there, let's say, not that it has to, but it then goes around, and then look at that, it comes back and ends at exactly the same point. So this blue curve on the left here is a closed curve. Is everybody with me? All right. Okay, so let's finish the definition here. What we mean when we say circulation. Circulation is just the value of that line integral in the special case that the curve is a closed curve. Line integral is circulation. Circulation is line integral for a closed curve. Okay. All right, so let's look at these examples. What is the circulation along this closed curve? What is the circulation of this vector? Oh, whoopsie. Let me choose a different color. This vector field here, like that, highlighted partially in purple. What is that circulation? Well, let's think through how I compute the line integral. The way I compute a line integral, and you could just look at it term by term, but remember, we have an interpretation of line integrals. Line integrals represent in some sense, the total amount that the fluid flows along the curve. And let's look at this picture. Along in there, the fluid is flowing very much along the curve. It's going exactly the same direction the curve is in that part of the curve. And then likewise here. The curve is kind of bent around to the left. Well, the fluid is correspondingly flowing that same direction in that vicinity. And likewise, everywhere sort of along the curve. So the fluid is flowing positively along the curve everywhere on this curve. And so grand total, I should expect to get a positive value for the line integral and therefore a positive value of what we call circulation in this example here. Everybody with me? All right. So now let's look at the next example. What about here? I'm going to have the curve start there, and notice I'm going I missed it. I'm going a different direction around the curve. It still comes back and ends at that same point, but having gone in a different direction. So now for this curve, let's talk what is the circulation. To what extent is the fluid flowing along the curve? Well, let's take along in here. Along in that part of the curve. The fluid is flowing like that. The curve is going like this. The fluid is going opposite of the direction of the curve. So along in here, the line integral is going to be negative. The contributions along that part of the curve to the line integral, negative. And then likewise, along in here. Again, it's parallel to the curve in exactly the wrong direction. So more negative line integral, et cetera, et cetera. Grand total, the line integral, aka the circulation. It's a sum of a bunch of negative contributions. The circulation negative. Everybody good? Okay. Now, do recall, when we talk about circulation, we're not talking about something that's just intrinsic to the vector field itself. Circulation is always asked with respect to a closed curve. So on this first example, when we say what's the circulation along this curve, another way to say it is, to what extent is the fluid circulating counterclockwise? Well, it is circulating counterclockwise. So yes, there's a positive amount that the fluid is circulating counterclockwise. On the other hand, on this question here, the curve is clockwise. So when we compute circulation along this curve, we're asking to what extent is the fluid circulating clockwise? And the answer is, well, it isn't. It's very clearly going counterclockwise. So, I mean, to what extent is counterclockwise clockwise? Well, it's a negative extent, right? And that's why we get a negative circulation. Does that make sense? Okay. All right. Sometimes it's really not clear. These first two examples that I've drawn here are idealized, right? We have the fluid is flowing around in perfect, the flow lines for this fluid, perfect circles. What are the odds, right? Real world, not so much. Furthermore, the paths along which I'm computing the circulations, perfect circles, centered at the center of the flow. So that's very idealized, it's very manufactured, and that's why we can kind of look at, at a glance and, kind of make sense out of what's going on in those cases. Sometimes it's just not easy. Oh yeah, your question, yeah. Yeah?
Is this at all related to curl?
Yes, it is. 100%. Yeah, that's right. But and there are some strong connections there, and in fact, that's going to be one of the big focuses of the next section of the book, and also a lot of chapter 7. But there's a lot to say there. So as much as I would love to go down in that direction, it's a massive digression, and we'll totally get to that. We're going to spend a bunch of time on that excellent question. Is that cool?
Yeah.
Okay. So I really will be better off just waiting on that. But you have great instincts there. So let's look at this example here, though. This curve. The center of the circle is not the same as kind of the center of the rotation of the fluid. And, well, I mean, it's just kind of weird here. If you look at the direction the fluid is going, at this point here, for example, the fluid is going that direction, which, if anything, is clockwise circulation on that curve. But if you look over here on the other side, and the field vectors are longer over there, on the other side, counterclockwise along that same curve. So here we have kind of competing terms. For a while, we have clockwise seeming circulation along the curve, and otherwise we have counterclockwise, and there's going to be kind of a opposing forces tug of war on which one of these is the bigger contribution. And so at a glance, in other words, it's not particularly clear here which is what's the circulation going to end up being, and thus the question mark down here at the bottom. Most of the time, you have to actually compute the integral. Most of the time, you have to compute the integral, and altogether, what the integral is telling you then is overall, what is that fluid really doing? And it's giving you information about that which is sometimes visually not clear. All right, now, why do we care about circulation? I'm going to give you two answers to that question. One that's easily relatable, one that's much more sort of like believably important. The one that's relatable, I like to imagine that you have, let's suppose you have pretend like this is September, and there's leaves falling, the leaves are orange, and here is a fallen leaf on the surface of a little river or a creek or something, and that leaf is floating on the surface, and then the water might be moving around it as it floats. And now, intuition, given this case right here, what do we think the leaf is going to do? And I propose that leaf is going to be spinning counterclockwise, because it's doing what the fluid tells it to do, and the fluid is clearly going counterclockwise, and so it seems believable that the leaf would be going counterclockwise. And I'm going to propose that the reason it's going counterclockwise more precisely is because if I look along the entire boundary and look how the water is pushing the leaf at each point on that boundary, each point on the boundary, the water is pushing it counterclockwise. So how the vector field points along the curve, namely what the circulation is, speaks directly to which direction is the leaf going to be rotating. Right? So I think this is a pretty easy pitch. It's pretty visually relatable. Circulation tells you to what extent the little object floating in the fluid is going to be rotating in the direction given or not. So again, keep in mind the direction of your orientation of your curve is how you're asking the question. So looking at this curve here, oriented counterclockwise, when I ask what's the circulation along that curve, I'm asking to what extent will my leaf be rotating counterclockwise? And the answer is it will be rotating counterclockwise a positive amount. Namely, it will be going counterclockwise. Whereas, if I were to look at this curve, same leaf, I'm just parameterizing the boundary differently. But because I'm parameterizing the boundary differently, I'm now going clockwise. I'm asking now the question, to what extent is my leaf rotating clockwise? Well, the water is still going counterclockwise. The leaf is still going to be going counterclockwise. So to what extent is that clockwise? Well, kind of the exact opposite of clockwise, right? It's counterclockwise. So it's a negative amount of clockwise. Way to interpret that calculation. Okay. All right. Last thing I want to say about this, and we're going to be out of time, and I'll have to be quick about this, but I'm not going to be able to go into all the details of this anyway. How do airplanes work? There's a lot to say about that, of course, but one of the big ideas of how airplanes fly is the shape of the wing. And I don't know if y'all have ever looked at taken a close look at the cross section of a wing. I don't mean as seen from above. I mean, looking at a cross section of the wing, and they tend to be kind of round in the front, and they kind of taper to where they're kind of sharp in the back. Right? So what's the deal with that shape, and why does that make the airplane fly? Well, there's a bunch of physics involved here. It turns out that when there is a flow of a fluid over a surface, that causes a force perpendicular to the surface. That's empirical. That's the Bernoulli effect, right? And it's just, it is what it is. So if we have an airplane wing shaped about like, let's see if I can do something plausible here. About like that, right? When the air is flowing over it like this, that creates a force, and the force is that way, roughly. Again, let's not worry about the details here. That produces an upward force. But here's the thing, there is also, let's see here, and I could say I'm computing that upward force by computing a line integral along that top part of the wing curve in that direction. So I get a positive amount of upward force. Okay, but what about the air that's going along the bottom surface of the wing? Right? Well, that's creating a downward force. It's creating a downward force. Right? Said differently, if I parameterize the bottom part of the wing that way, that tells me downward force. So then I make the following switcheroo. I say, okay, well, what I want to compute actually is all upward force. I want the grand total net, however you want to say it, upward force. So I don't want to compute a downward force. I want to compute an upward force. So I'm going to turn this arrow around backwards by parametrizing this bottom part of the curve backwards. And that gives me then that direction along the bottom surface of the wing, computing upward force. Grand total then, the grand total upward force computed by the wing is a line integral around this closed curve, namely the closed cross-section of the wing. A vector line integral on that closed purple cross-section curve is what computes the total lift of the wing. So this is a massive, tremendously important application of vector line integrals, leaving out tons of details, of course, right? But vector line integrals are the tool that you use to compute lift for airplane wings. And so I think that's pretty persuasive that vector line integrals, and furthermore, in the context of fluid flows, right? This isn't a computation of work. This is how we're using fluid flows to compute something really important. And like I say, I think that's believably important. I mean, if you believe airplanes are important, then vector line integrals and fluid flows important. That's a good place to end it. Let's call it a day right there. So drawing the line right here. Y'all have a good day. See you later. See you on Wednesday. Let's see here.